Well, this is a redux of the postulates of quantum mechanics, which we've had earlier in the class. But this time we'll do the fancy Dirac notation version. So they're very similar, just modulus of notation. Uh, First of all, is the existence of a state function, state vector. To each physical system, there corresponds a state vector or a psi ket that contains all the information that it's possible to know about the system. So everything is buried in that. And once you have complete knowledge of this ket vector, this ket state vector, then it's just a matter of extracting it from that once you know what that is. To every physical observable g, so g might be momentum, for instance, there corresponds a Hermitian operator, as indicated by the g operator, such that g operating on a state gives the value of the value for that g for that state times the ket back again. Okay? Now here, the g ket is the eigenstate or the eigenket corresponding to this operator g, and little g here is a number. In fact, it's a real number. Yeah? It has to be a Hermitian operator, and I know that Hermitian operators have real eigenvalues. So eigenvalue here, g, corresponding to the eigenstate or the eigenvector, eigenket vector g. The time evolution of the state vector of the system is determined by the Schrodinger equation. And here we'll write it in this form, in operator form. H is the Hamiltonian operator. It's Hermitian, a very special one that generally corresponds to the total energy of the system. And we had the Born hypothesis. That was this probability assumption. And I'll just list it in 1D. In one dimension, the bracket, and here we've got x times the state function, or operating the inner product of the position with the state function gives us the wave function psi of x and t. And now you have to think of this x here as the component of the state vector, the state ket, in the x direction. This projects out the x component of it, and this x here really is a different kind of label. It's a continuous label, but it really is like a component. And this gives the probability amplitude, the psi here, or this projection on x. Probably the way we stated it before was if you take the absolute modulus of that, the complex psi times complex conjugate of psi times psi, then you get the square of this projection into the x coordinate, psi star psi or psi squared. Then either one of those quantities is the probability density for finding the particle. There's an expansion postulate, is that once we've found these g's, and let's go back up here, I'm still talking in terms of this case here. I've got an operator, a physical variable operator, operating on an eigenket, giving me the eigenvalue times the ket back again. Then when one solves this eigenvalue problem, you get not only the corresponding eigenvalues, but also a set of eigenkets. And the expansion postulate says that set over all G of all the eigenkets forms a complete orthonormal basis, so that any state vector can be written as an expansion about in terms of that. This is really These eigenkets are kind of like unit vectors, and this is like a vector over here, and then these would be the components in each one of these unit vector directions. So that's the expansion postulate. So any state, physical state of the system can be expanded on that basis set. The measurement postulate is extended a little bit here. If a system is in the state with this eigenkit, or this state vector kit, then the probability that a measurement finds the system in the state G, one of these eigenstates in this case, or really this could be any state, is just the inner product of G with that state psi, and then you take the absolute square of it, then that gives you the probability of a measurement that finds the energy in that state G with the eigenvalue G. Yeah. And then finally, the collapse postulate is after a measurement of G that returns the value, a specific one, say G1. So I'm going to measure a physical quantity like momentum, and then I return a specific value of the momentum, maybe, I don't know, maybe 20 kilogram meters per second. Yeah. So this is a specific value. But it has to be one of the eigenvalues, so it returns an eigenvalue, a measurement returns an eigenvalue, and then afterwards leaves the system in that state of the eigenvalue that it was measured. If you come back and subsequently measure the system, it will give you G1. Well, those are sort of the dressed up versions. When you go to a formal party, you get dressed up. So if you go to formal quantum mechanics, then they usually express these in terms of Dirac notation, and as a result, these systems, this postulation of it may be of value to you. Really no different than the ones that we've had earlier. That's just using a slightly different and more general notation to present them.